All right, let's begin our last type of related rates word problem questions. So the last shape that we need to tackle is a cone. And the reason why I like to save that for the end is because there is multiple parts that are changing. It's not just either the volume or radius or height. Everything is changing at one time. So as we look into it, you'll see kind of why this one is saved for last, because they're a little bit different almost every time. Okay, so we're in packet number 1. So if you go to the related rates day 1, we are in, I believe it might be page 5, which is you are filling the cone with water. So I think it's right before the triangle one that we did. So we're going to start with drawing a picture and then determining how they're related, how the radius and height are related. So we'll start with drawing a picture of a cone. So in case you forgot what a cone looks like, it could be base down or base up. So the base is a circle, okay, and then it has a triangle as maybe the top or the bottom. So it could also look like this with a circle and we have a triangle here. Okay, so that is what a cone looks like. And they want to know how are the radius and the height related. And so what that means is just what is happening as we are filling this cone up. So as the volume, if we were to fill this cone up, so let's say this was a paper cup. You've ever seen those paper cups out of like a water machine maybe, where you fill them up. So let's say this is happening. So as the volume increases, as we fill this up and we start to put water into it, the radius is going to increase, right? Because your circle is getting larger and larger. There's just like a bunch of circles here on top of each other. So the circle's radius is getting larger. The height of the cone, the height of the water is also changing. So the height is also increasing. And then obviously the volume is also increasing. So the radius, height, everything is increasing at the same time. But the difference here is, remember the cone from last class, the radius stayed the same in the cone, but this time the radius is going to increase or decrease. So if you were draining it, then the radius would decrease, the height would decrease, the volume would decrease. So that's the difference between this one and the ones that we did in the last class. Nothing is going to be constant here. Everything is going to be changing. Okay, so what parts are changing over time? So all of them. So that means that everything is changing. So we have the derivative of the height. So the rate of the height in terms of time. We'll have the rate of the radius in terms of time. And we'll also have the rate of the volume in terms of time. So all 3 of them are changing. There is no constant. So again, it is unlike the 2 we did last time with the Pythagorean theorem and the cylinder, where we had the radius or the hypotenuse was a constant. There's no constants here. They're all changing. Okay, now if you might not remember what the formula for the volume is of a cone, so we'll go over that again. So what we'll be using here and what we'll be differentiating is going to be, so it is very similar to the cone. So if you remember, or not the cone, the cylinder. So the cylinder, if you remember, was pi r squared h. Pi r squared h. So the difference is here, and just because I know you might like to understand where it comes from. So remember, this was what the cylinder looked like. And so basically you can fit, if you look at this, here's a cone that's inside of a cylinder. And so roughly, if you notice, there's 3 cones that are inside this cylinder, right? So that means that the volume for the cone is 1/3 of the volume of the cylinder that cone would fit in. Pretty neat, huh? So that is the formula that we are using, is 1/3 pi r squared h. So it is the formula of the cylinder, but we're just taking 1/3 of it because, again, 3 cones can fit into a cylinder. Okay, so let's move on to our packet 2. So I have on the next slide here, we're going to move on to packet 2. You're going to go to problem number 4, which this is the problem for you. I already put it on and typed it in so we can get started right away. I'll give you a second to find it. So packet number 2, problem number 4, not individual problem number 4, problem number 4. So we have a conical tank being filled with oil at the rate of 5 feet per second. The radius, if the radius is 3 times the height, how fast is the volume changing when the height of the oil in the tank is 25 feet? So let's talk about what we know, okay? So we have a conical tank being filled with oil at the rate of 5 feet per second. So the 5 feet per second being filled with oil. So what's happening there, that is the height that is changing. Okay, so the height is being changed at 5 feet per second. So that is dH dt. Okay, so dH dt equals 5. We know that. Okay, the radius is 3 times the height. That's important. So I'm going to write that in here. The radius is 3 times the height. How fast is the volume changing? So the rate of the volume is what we're looking for here. Okay, so that's the question mark. That's in question. When the height of the oil is 25 feet. So the height is 25 feet. Okay, now previously, if you remembered, I told you that we cannot plug anything in until we differentiate. And that is true, except in this exception. And here's why. Let's go ahead and put the formula. So we have volume equals 1/3 pi r squared H. Okay. So before we differentiate this, the reason why we can plug something in here is because we know something, we know a value in terms of another variable, and that's a different game. So here, the 5 and the 25, those are values that are important to the instant of the change, right? But this value, the radius being 3 times the height, it is a variable in terms of another variable. And so because it's a variable in terms of another variable and not a distinct rate or a distinct moment in time of the height or the radius, we can plug this in before we differentiate. And the reason why we want to do this is it's going to make our life a lot easier. We won't have to use the product rule anymore when we differentiate. So we're going to plug the radius in here, for the letter R. And when we do that, what'll happen is we get rid of one of the variables and we will have everything in terms of just height. So that will make our lives easier. So if I plug that in, I'm going to get V equals 1/3 pi and then 3h squared times h. So 3h in parentheses squared times h. So again, the only reason we can do this is because it is a variable in terms of another variable. And then what it'll do for us is it'll put this in terms of just h instead of r and h, then we don't have to do the product rule when we differentiate. Okay, so now doing some algebra, 3h times 3h, because that's 3h squared, 3h times 3h is going to give me 9h squared. Okay, so I have 9h squared, and then we have to multiply 9h squared times another h. So that'll give me 9h to the third power. So now I have 1/3 pi times 9h to the third power. And now this looks funny. I don't like it like this. So I'm going to put the 1/3 and the 9 together. So that'll give me 1/3 of 9, or 1/3 times 9 gives me 3. So my volume is 3h to the third, or 3 pi. Sorry, let's do 3 pi. Rewind that. Okay, so 3 pi and then h to the third. So here at this point, now I can differentiate. So before, again, I was just putting this in terms of something else. So now right here is where I differentiate. Okay, so take the derivative at this point if you want to write that down. Now here's why it's different, is because next problem, this might be a different situation. And so you have to plug in first and then differentiate. So there's not a set formula that you're going to use every time. You have to find your formula with this when you plug in your R or your H, because next time it could be the H that you plug in. So now if I differentiate this again in terms of time, so the derivative of V is just going to be 1 dV dt. And then I differentiate in terms of H. So I'll bring 3 times 3 will give me 9 pi. h squared, and then dh dt, because again, we are differentiating the variables in terms of time. These are rates. Okay, so now that we did the differentiation, so plugged in was step number 1, plug in. Step number 2 would be differentiate. And now step number 3 would be, now we can plug in our actual values. So dv dt, we don't know what that is, so we'll leave that as dv dt equals 9 pi. And then we know our h is 25, so 9 pi times 25 squared. And then dh dt is 5. Okay, so if we multiply this all out, so 25 squared times 5 times 9 is going to be, and you might want to just double check my work, but I got 28,125 pi. And that would be feet cubed per second. Okay, and I mean, it makes sense because this is a huge tank. It's saying it's filling in 5 feet per second. Think about 5 feet per second. That's about, think of a 5-foot person that's pretty tall. So this is a big, big tank. It's an oil tank. Okay, so that is your answer. 28,125 pi feet cube per second. Okay, let's try one more, just so you can see how it does change every time with what you're doing. So let's turn to, in the same packet, we're turning to the CUDA worksheet, which is the last worksheet attached. And that is going to be number 3. So on the front of the very last page, number 3 at the bottom, says a conical paper cup is 10 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? All right, lots of things, lots of things. So let's go through the numbers here. What we got? So a conical paper cup right now, so if we just measured it right now with no water in it, it is 10 centimeters tall. So that means the height is 10 and the radius is 10. Okay, so that's just the normal dimensions without filling it. The cup is being filled with water so that the water level rises. So the rising is the height at a rate of 2 centimeters per second. So that means the rate of the height, dh dt, because it's rising, it's being filled, is 2. At what rate is water being poured into the cup when the water level is 8 centimeters? Okay, so water level 8 centimeters means the height is 8. All right, at what rate is the water being poured? So that means, again, we're looking for the volume in terms of time. That's our question mark. It's our unknown. All right, so this may be a little confusing because if you notice, we have 2 different heights. But hopefully that you at least gauge that this is the, I don't want to say the constant, but this is the actual height and radius of the paper cup. They want to know what is like what's happening when the height is only 8, not when it's 10, when it's 8. So this is the information that we're going to use to help plug in at the very beginning. So remember, step number 1 is we need to plug in for another variable in order to get rid of a different variable. So 1/3 pi r squared h. Okay, so we need to find a relationship between the radius and the height so we can plug it in and figure it out. Okay, so the relationship here, they didn't tell us like last time they said the radius is 3 times the height. They might say the height is half of the radius. And that's how you know what you would plug in. This time they didn't tell us that, but look what they did tell us. What do you notice about the height and the radius? Hopefully you notice that they're equal to each other. So that means that the height equals the radius. So h equals r, or r equals h. But how do you know, do I plug in my h to get rid of my r? Or do I plug in my r to get rid of my h? Like, which one do I plug in? Well, look at what they gave you down here. They gave you that the height was 8. So you don't want to plug in R for H and have this in terms of the radius, because then you don't have anything to plug in for the radius. So we want to plug in H into R into this spot. Because again, if we were to plug in R into H and just have the letter R, when we differentiate, we won't have anything to plug in. Okay, so we're going to plug in here our H for our R. So all that's going to turn into is, instead of R squared, it's going to be H squared, which what does that do then to H squared and H? That'll give us 1/3 pi R, or sorry, pi H to the third power. Okay, so now this is the formula that we're going to differentiate right here. Now we can differentiate this. Okay, take the derivative of this one. So we'll multiply 3 into 1/3. Oh, sorry, we got to do dv dt. So the derivative of v is just dv dt. And then 3 times the third just cancels out to be 1, or you can just write pi h squared dh dt. Ooh, whoa, a little crazy there. Dh dt. Okay, so now after we differentiate, now we can plug in these values into our differentiated formula. We don't know dv dt, that's what we're trying to find, so we're going to leave that here. Okay, equals pi. We know that h is 8, so pi times 8 squared times h dh dt, which is 2. So if I multiply this out, it would be 64 times 2, which gives you 128 pi. And then that would be 128 pi centimeters cubed per second, because this is volume. Okay, so that is it. That is the 2 examples for you for the cones. Hopefully that makes a little bit of sense, but just remember, it is different. You are going to plug in something, either the radius or the height, a variable in terms of another variable, to get rid of the variable before you differentiate. Then you differentiate, then you plug it in. All right, good luck. If you have any questions, let me know.